All right, so get this. We're diving deep into quantum spiking neural networks today.
QSNNs.
QSNNs, yeah, exactly. It's basically like computers that can think like our brains, but with the whole quantum mechanics thing thrown in.
Yeah, it's a pretty wild idea.
Wild is an understatement. We're working off an essay, by the way, by Jorgo Schneeppert. It's called QSNNs, Quantum Spiking Neural Networks for Chi-I.
That's a great one. Yeah, there's a lot of fascinating research happening right now in this area.
Right. I mean, just imagine like solving problems that would normally take forever, like, I don't know, insanely complex optimization problems or image recognition and speech recognition that's, way more powerful than anything we have now.
Yeah, and it goes even further than that. Robotics, communications, even cryptography could all be revolutionized by this tech.
Definitely a total game changer. But I think we need to back up a sec. Like, to really get QSNNs, we got to start with the basics. I mean, everyone's heard of AI these days, right? Powering all kinds of stuff.
Right, from voice assistants to image recognition, all that's powered by artificial intelligence.
And, I know those usually use neural networks, which are kind of based on the structure of the brain, right?
Exactly. It's like taking inspiration from the brain, but simplifying it so computers can handle it.
Okay, so that's our starting point.
Yeah.
But where do these spikes come in? What makes them so special?
So those standard neural networks, they work with this constant flow of data.
Right. Always running, always processing.
Exactly. But in spiking neural networks, we call them SNNs for short.
SNNs. Got it.
In SNNs, the information is sent in these pulses.
Pulses?
Yeah, or spikes, just like actual neurons in our brains.
Oh, so it's not a constant stream. It's more like these short bursts of activity.
That's it. And that actually makes them way more energy efficient, which is a big deal.
I can see how that would be a plus, especially with all the talk about reducing energy consumption.
And they're also much better suited for tasks that need to happen in real time, imagine a self-driving car needing to react instantly to something in the road.
Right. Makes sense. So we've got the neurons firing in these quick bursts. Okay.
Yeah.
Got it.
Yeah.
But now we got to add in the quantum mechanics part.
Right. And that's where things get really wild.
Quantum mechanics 101 time. What are the key ideas I need to know here?
All right. So the two big ones are superposition and entanglement. Have you ever heard of a qubit?
Qubit. Is that the quantum version of a bit?
You got it. But here's the thing. A normal bit can only be a 0 or a 1.
Like on or off, right?
Exactly. But a qubit, thanks to this thing called superposition, it can be both 0 and 1 at the same time.
Both at the same time? How is that even possible?
Well, it's kind of like, imagine you flip a coin.
Okay, I'm picturing it.
While it's spinning in the air, before it lands, it's kind of both heads and tails at the same time, right?
Yeah, I guess so.
It's only when it stops that it settles into one state or the other. That's kind of what superposition is like.
So it's like the qubit is in this fuzzy, uncertain state until you measure it.
Exactly. And that ability to be in multiple states at once is what gives quantum computers so much potential power.
Okay, I think I'm following you.
Yeah.
So superposition, check. But now, what about this entanglement thing?
All right. Now, entanglement. This is where things get really, really mind-bending.
Bring it on. I'm ready.
So imagine you have two of those spinning coins, right? But they're linked somehow.
Linked. Magically connected.
Well, not magically, but quantum mechanically. And no matter how far apart they are, even if they're light years away.
Light years? That's crazy.
No. If one lands on heads, the other one instantly lands on heads too. And if one lands on tails, the other one flips to tails. Instantly.
No way. So they're mirrored even across huge distances.
Exactly. It's like they're communicating with each other faster than the speed of light. Einstein called it spooky action at a distance.
Spooky is right, but how is that even possible?
It's just how the quantum world works. And this entanglement, it turns out, is key to unlocking some of the most incredible possibilities in quantum computing, way beyond what we can even imagine with regular computers.
Okay, so my brain is officially starting to hurt. We've got neurons firing in these quick bursts and qubits doing their mind-bending quantum thing. But how do those two worlds actually come together in a QSNN?
That's where the real magic happens. So in a QSNN, we're not just talking about neurons as simple on-off switches anymore.
Right, they're more than that.
They're actually treated as full-on quantum objects.
Quantum neurons, wow.
Yeah. And their state, it's not just a 0 or a 1, it's described by this thing called a wave function.
Okay, wave function, I need you to break that down for me.
Well, it's basically a mathematical description of the neuron's quantum state.
Okay, I'm going to trust you on the math for now.
No problem.
Yeah.
But the key thing is, when a neuron fires, when it creates that spike, it's not just sending a signal, it's actually making a shift between those different quantum states, like those spinning coins we talked about.
Ah, So the spike isn't just a message. It's like changing the entire state of the neuron on a quantum level.
You got it. And because it's a quantum system, that means it can explore all those possibilities, all those states at the same time, thanks to superposition.
Okay, I think my mind just officially blew up.
Mm-hmm.
So we've got these quantum neurons firing off these spikes.
Mm-hmm.
But how do they all work together? How do they actually process information?
That's where quantum gates come in.
Quantum gates.
Yeah, you can think of them kind of like the logic gates in a regular computer. They're the building blocks of computation, but instead of working on bits, they work on those crazy qubits.
Right, and they're doing those quantum operations like superposition and entanglement and all that.
Exactly, and they allow us to do stuff that's just impossible with classical logic.
Like what kind of stuff?
Well, imagine being able to adjust how likely a neuron is to fire based on the entire network state.
Not just what's right next to it.
Exactly. It's like the neuron is connected to everything at once, in a way, and it's this interplay between these quantum gates and the timing of those spikes that really defines how information flows through the whole QSNN.
So it's not just about the connections, it's about the timing, too.
Yeah, it's like a quantum symphony, all these neurons firing and interacting in this complex, perfectly timed dance.
Okay, I'm definitely getting the sense that building one of these QSNNs isn't as easy as, like, coding up a neural network on my laptop.
You're telling me we're talking about needing some pretty serious hardware here, like quantum computers, which, let's be honest, they're still pretty much in their infancy.
So it's not just about the theory, it's about actually being able to build the darn thing.
Right. And that's where a lot of the challenges lie.
Okay, well, I think we've officially entered the deep end of the pool here. We're talking about quantum mechanics, we're talking about spiking neurons, we're talking about computers that could potentially be smarter than us. Where do we even go from here?
Well, that's what we're going to dive into next. We'll tackle the challenges, the potential applications, and all the wild possibilities that QSNNs open up.
Buckle up, everyone. Things are about to get even weirder.
So as we were just saying, QSNNs, they kind of need quantum computers to actually work, and that's like a huge challenge right now.
Yeah, I mean, we hear all this buzz about quantum computers, but they still seem pretty mysterious. Like, what makes them so hard to build?
Well, one of the biggest things is that those qubits, remember those?
Yeah, the spinning coins?
Exactly. Those quantum states, they're super delicate, like crazy fragile.
Fragile how?
Well, like, they can be messed up by the tiniest things, you know, like vibrations, even like slight temperature changes, stuff like that.
Oh, wow. So it's like trying to build a house of cards in a windstorm or something.
Pretty much. It's not just about making bigger quantum computers with more qubits. It's about making those qubits more stable.
More robust, less prone to errors, right?
Exactly. And that leads us to the whole issue of error correction.
Okay, error correction. What's that all about?
Well, in quantum systems, errors are basically unavoidable, kind of like static on a phone line.
Annoying.
Totally. So we need to come up with some really clever error correction methods if we want QSNNs to actually be reliable, you know, get consistent results.
It makes sense. So it's like this constant battle between pushing the boundaries of what these quantum computers can do and also making sure they're like stable and dependable.
Exactly. And then there's the whole energy consumption issue, you know?
Right. We talked about how SNNs are supposed to be really energy efficient.
Right, because of those spikes.
But quantum computers, from what I've heard, they use a ton of power, right?
Yeah, that's a big challenge. I mean, it kind of defeats the purpose if we create these super efficient SNNs and then run them on these energy-hungry quantum computers.
Right. Kind of undercuts the whole thing. So are there ways to like make QSNNs more energy friendly?
Well, that's a big focus of research right now. One idea is to like create these hybrid systems. Yeah, like combining the best of both worlds. Maybe some tasks like the initial processing could be handled by regular energy efficient SNNs, and then the really heavy duty quantum stuff would go to the quantum computer.
Oh, that's interesting. Like splitting up the workload.
Exactly. Delegate the tasks strategically. And then there's research into making the quantum computers themselves more energy efficient.
Oh, really? How are they doing that?
Well, they're experimenting with all kinds of new qubits, ones that are less sensitive to noise and need less energy to run.
So like more robust qubits that don't freak out so easily.
Exactly. One promising area is this thing called topological qubits.
Topological qubits, that sounds intense.
They're, in theory, much more stable than the qubits being used in most quantum computers now.
So, like, less static on the line.
Something like that. It's all very cutting edge, lots of different approaches being tried.
It sounds like there's a ton of work still to be done, but it's also pretty exciting.
Right.
You know, like Despite all the challenges, it seems like the potential of QSNNs is just massive.
I totally agree. We're still early in the game, but the research is already pointing to some truly revolutionary applications.
Okay, well, let's dive back into those applications then. I want to hear more about how this stuff could actually be used, like real-world examples.
All right, let's do it.
Let's start with optimization problems. I remember you mentioning those earlier.
Right. Well, imagine like a logistics company. Okay. They're trying to figure out the absolute best routes for their trucks, hundreds of trucks.
Across a whole network of roads, yeah.
Exactly. And this is actually a classic problem in computer science called the traveling salesman problem.
The traveling salesman.
Yeah. It's basically trying to find the shortest possible route that hits all the different destinations, and it gets exponentially harder for regular computers to solve as you add more destinations.
Right. Like with just a few stops, no big deal. But once you have hundreds or thousands, forget it.
Exactly. But a QSNN, it could leverage superposition, remember?
Yeah, being in multiple states at once.
Right. It could explore all those possible routes simultaneously.
No way. Like a quantum GPS that calculates the best route for every truck at the same time.
Something like that. Finding the most efficient solution way faster than a classical computer ever could.
Okay, that's pretty impressive. What about image and speech recognition? How would QSNNs change those?
Well, think about it. A QSNN, it doesn't just see an image like we do. It could actually analyze the quantum states of the image itself.
The quantum states. So like going deeper than the pixels.
Way deeper. Potentially detecting anomalies like at the subatomic level, things we could never see with current technology.
Wow. So it's like having quantum-powered vision.
Exactly. And for speech recognition, imagine a QSNN that could pick up on the tiniest, most subtle nuances in a person's voice.
Like stuff we wouldn't even consciously notice.
Right. Maybe even detecting emotions or health changes, things like that.
That's wild. Okay, what about robotics? How would QSNNs affect that field?
Well, I think one of the biggest impacts could be creating robots that are way more adaptable and responsive than anything we have today.
More intelligent, basically.
In a way, yeah. Imagine a robot that can learn new tasks super quickly.
Like on the fly.
Exactly. And adjust to new situations instantly, like in real time. Think about robots working in factories with humans, or search and rescue robots in disaster zones. They need to react instantly to unpredictable environments.
Right. It's not like everything's pre-programmed. They need to think for themselves.
Exactly. And with those quantum-enhanced senses we were talking about earlier, they could do things like locate survivors or avoid hazards in really complex situations.
It's like giving them a whole new level of awareness and understanding.
Exactly. And the possibilities go even further. Remember, Schneppat's essay mentioned quantum communication and cryptography.
Yeah, that was pretty mind-blowing.
Well, think about this. One of the biggest challenges in quantum communication is sending quantum information over long distances without it getting, messed up.
Right, it's super delicate.
Exactly. But QSNNs could help us build better quantum repeaters, basically devices that boost the signal and help keep the quantum information intact.
Oh, so it's like having signal boosters along the way to make sure the message doesn't get lost.
You got it. And in cryptography, QSNNs could be used to generate truly random numbers.
And why is that important?
Well, random numbers are super important for creating encryption keys, the codes that keep our data secure.
Right, I've heard about that. Like, the more random the key, the harder it is to crack.
Exactly. And QSNNs could also lead to whole new types of encryption that are resistant to attacks from, future quantum computers, which could potentially break the encryption we use today.
So it's like future-proofing our data security.
Exactly. It's a really fascinating area.
Yeah, it's like not only can QSNNs bring about this new era of super secure communication, but they can also help us stay ahead of the curve, make sure our data stays safe even as technology keeps advancing.
Right. It's all about staying one step ahead.
Well, my brain is officially fried. We've covered so much ground already.
I know, right? It's a lot to take in, but it's just the tip of the iceberg when it comes to QSNNs.
Well, lucky for us, we have a little more time to keep exploring this.
Yeah, we still need to talk about the bigger implications of this technology and what the future might hold.
Right. The big picture stuff. So everyone stay tuned. We'll be right back after a short break. All right, welcome back to our deep dive, I guess you could call it, into QSNNs. I feel like we've been through a lot.
We have, from the nuts and bolts of how these things work to all the, mind-blowing potential applications.
Yeah, it's been a wild ride for sure. But before we wrap things up, I think it's important to zoom out a little bit. think about the big picture.
The big picture, yeah, I like that.
What are like the broader implications of this technology? How could QSNNs actually affect, society as a whole? I mean, we've talked about specific applications.
Right, like self-driving cars and quantum cryptography and all that.
Exactly. But the impact of something like this, it's got to go way beyond just like individual use cases.
Oh, absolutely. I think often when we talk about new technologies, we get so caught up in the, what can it do part that we forget to ask the what does it mean part.
Right. The philosophical side of things.
Exactly. So like, what are some of the big questions that QSNNs raise? Are there, ethical or philosophical implications we need to be thinking about?
I think that's a really important point. So, like, what kind of stuff are we talking about here?
Well, I think one of the most fundamental questions is how QSNNs might change our understanding of, intelligence itself.
Intelligence. That's a big one.
Right. Like, could these systems, these things that are based on the human brain but powered by quantum mechanics, could they actually develop forms of intelligence that, like, rival or even surpass our own?
That's a question that's been around for, like, forever,
Yeah.
right? Ever since we started thinking about artificial intelligence.
Right. But QSNNs, they definitely add a whole new dimension to that conversation.
Yeah, I mean, we're not just talking about, like, computers getting faster or better at processing information.
It's something potentially much more profound.
Right, like a fundamental shift in what we even consider intelligence to be.
Exactly. And as these systems become more and more sophisticated, we're going to have to grapple with these really complex questions.
Questions about, like, consciousness, sentience, free will.
All of that. And it goes even beyond just, like, the definition of intelligence. It touches on the very nature of, what it means to be human.
Wow. Okay, so we're getting pretty deep here.
It's unavoidable, really. We're talking about technology that could potentially reshape our understanding of ourselves and the universe.
Right. And I think it's important to acknowledge that there are potential risks too, right? I mean, with any powerful technology, there's always the possibility for misuse.
Absolutely. We have to be mindful of how QSNNs could be used, both for good and for, not so good purposes.
So, like, what are we talking about here? Give me some examples.
Well, imagine, like, using QSNNs for, manipulating people's thoughts or behavior, or creating autonomous weapon systems that can make decisions without any human oversight.
Okay, yeah, those are some pretty scary scenarios.
Right. And those are just a couple of examples. There are probably tons of potential risks that we haven't even thought of yet.
It's like as we push the boundaries of technology, we also push the boundaries of what we need to be concerned about.
Exactly. And that's why it's so crucial to have these conversations, to think about the ethical and societal implications of this technology right from the start.
So it's not just about, like, the scientists and engineers in the lab, right?
Right. We need a much broader conversation involving ethicists, policymakers, the public, everyone.
So, like, a collective effort to ensure that QSNNs are developed and used responsibly.
Exactly. Technology shouldn't be developed in a vacuum. It needs to be guided by our values, by our shared understanding of what's best for humanity as a whole.
Well said. I think this has been an incredibly thought-provoking look into the world of QSNNs. We've gone from, like, the nitty-gritty technical details to these big philosophical questions about intelligence and the future of humanity.
Thanks to Jörg O. Schneppat and their essay, we've been able to take our listeners on a pretty amazing journey.
Yeah, it's a journey that's just beginning, really.
No, absolutely.
Yeah.
The quantum future is unfolding right in front of us, and it's up to all of us to shape it, to make sure it's a future that benefits everyone.
Well, on that note, I think it's time to wrap up our deep dive. To all our listeners out there, keep exploring, keep asking questions, and keep the conversation going. The future of QSNNs and the future of AI itself is in our hands. Thanks for joining us on the deep dive.